This is now the second installment of the lectures on Fourier transforms in one dimension. We're actually going to cover three topics today. We're going to talk about the convolution property of Fourier transforms. We're going to talk about the sampling function, and on the basis of that, we'll talk about a concept that comes up pretty often in CryoEM image processing, and that is the Nyquist frequency. But first, let's get to last time's homework. So I asked you to solve this problem, the sum of two Gaussian functions that are displaced from each other, and that's the Fourier transform. Now, hopefully you got that. Let's just see how one gets that. So here's our g of x. It's e to the minus pi x displaced by 2 units. Plus e to the minus pi x displaced by 2 units in the other direction. And we know what the Fourier transform of a Gaussian function is. It's a Gaussian, but we need to invoke the shift theorem because we've shifted these away from the origin. So this first one looks like e to the minus pi u squared times the shift phase term, which looks like e to the minus I 2 pi u d, where in our case d happens to be 2. That's the size of the displacement. And then this other term is going to be exactly the same, except that it's going to be e to the plus I 2 pi u d, and I can just collect these together. So I have this Gaussian and then times these two complex exponentials. Now, when you see that, I mean, that is, strictly speaking, the answer to our homework. But when you see that, you should say, aha, immediately this is going to simplify because I have a number and its complex conjugate added together. So remember that this complex exponential is a cosine and a sine function. So it's cosine of 2 pi u. Start that over. This complex exponential is equal to cosine of 2 pi u d plus sine I times sine of 2 pi u d. And there's a minus sign there, so there's a minus sign there, or I'll put a minus sign here. And this one is just the same. It's just the same thing, but with a plus there. And so these two, when I sum them together, the sine term goes to 0, and we're just left with the cosine term. And we have two of these cosines added together. So the final answer is e to the minus pi u squared. G of u is e to the minus pi squared times 2 times cosine of 2 pi u d, and d being 2, so this is just 2 pi times 2u. So that's the function that we got, and you can see what it looks like. It has an envelope that looks like our favorite Gaussian function, and then it's multiplied by a cosine, so it has these oscillations in it. All right, so much for the homework, and now I want to talk about convolutions. We'll make use of this of these functions a little later, so it's good that you did your homework. We're going to talk about convolution. Convolution is a very important concept that is going to show up a lot in modeling imaging systems and in image processing. Electrical engineers think a lot about convolution in terms of filters. So you have some kind of box that you call a filter, and in comes some input signal, and out comes some output signal. And the filter is described by a called filter kernel that I will call H of S. And an example of an h function might look like this. So this is s, and that's h of s. And here's what a filter does. So if the input signal has a delta function in it, then the output signal has something that looks just like h of s coming out. If the input is two delta functions, then the output looks like two superimposed copies of h of s. And so if we have a whole series of delta functions, you can see how this would kind of build up. But another way of doing that is say, okay, let's put in a rectangular pulse. And what will happen over here is that we will get then a smoothed off rectangular pulse. And you can imagine how that would work, because if you model the rectangular pulses closely spaced delta functions, it will build up and decay like that. And in general, you give me any sort of signal, and out will come a signal that is, in this case, kind of smoothed off. Now, what the filter is doing is it's performing a convolution operation. And you're not going to like this, but here's what convolution looks like. If we have two functions, g and h, and we convolve them with each other, what we're really doing is taking an integral that looks like this: g of x minus s, h of s ds. And we can think about what this convolution operation does when we look at, say, this signal, and we look at our kernel h. And what happens is, if this is the input, we'll call this g of x, and our kernel looks like that. And here's our output function. How do we get the output function? So what we do is to compute a particular output point, what I'm going to do is I'm going to take a variety of points from the input. I'm going to start with the point right here at, so this is point x in the output, and this is point x on the input. So I start out with taking the value right there at x, and I will multiply it by this value of the h kernel function, h of s. And then I will look a little bit farther back. So here is x minus s will go back to this point, and we will take a weighted value of that, and we will add it in. But as we go back further and further, as s becomes bigger, and we're sort of looking back further and further, the size of the weights gets smaller, and that's because the weights are determined by h of s. The weights are determined by that, and so the output here is going to be whatever sum we get from combining this weighted average of the input points, and we'll get, a point something like this. And if we go and compute more of these points, we will then see the gradual rise that we got there. So that's how the convolution integral works. Convolutions are numerically kind of expensive, because for every value of x, you also have to compute for every value of s. That's not too hard if you have 100 values of x and s, but if you're trying to do a convolution in, say, a large three-dimensional volume, there might be a billion x values, and there might be a billion s values, and that integral could take many years to compute. But people use Fourier transforms, and so there is a Fourier convolution theorem that is very, very important and very, very useful. And it's even going to allow us to do deconvolution. So to add to my list of Fourier transform properties, remember last time we had linearity, scale, shift properties. So I'm going to add one more of these, which is convolution, which says that if I form the convolution of f and g, the Fourier transform of that is just f of u times g of u. So this complicated integral in the x domain becomes just a point-by-point multiplication in the u domain, and that's why this property is so beloved. So here's another example. This is now the convolution of a collection of various little functions being convolved with that particular kernel. So we have a rectangular pulse. This is the sort of foot of a delta function, and here is some random signal, and you can see that everything's been kind of smeared out. Now, the convolution theorem, as I said, says that in the Fourier domain, the convolution is just a multiplication, and we can derive this if you really want. Here we go. We're trying to compute the Fourier transform of this thing, and so we do a trick where we split the exponent into two parts and do a substitution of one of the variables of integration. What we wind up with is, here's the Fourier transform of g, and here's the Fourier transform of h. And so we show that it's the product of those two Fourier transforms. So in computing this, here's how I did it using Fourier transform. So I took this signal and I operated on it with a Fourier transform in my computer. The red here is the real part and the blue is the imaginary part. And here is the Fourier transform of my Gaussian pulse. It's a real Gaussian. And so what I do is I just point by point multiply this by that, and I get this. And you can see that the main effect of multiplying by this h of u is to dampen the higher frequencies, higher values of u, down to 0. And when I do the inverse Fourier transform, then I get the smoothed out values. So now that we know about this theorem, this raises a very interesting question, which is, can we undo a convolution operation? Suppose I gave you this function, and I told you that's the kernel. Would we be able to reconstruct the original function? So that's, in general, a difficult problem. It's not always solvable because, just think about it, we have to reproduce all of the zigs and zags of that original g of x from this heavily filtered and smoothed output function. But here's what we know. We know that the output function, f of x, it's the convolution of g of x and h of x. And so we know its Fourier transform is just g of u times h of u. And that means that we could recover, given f, we could recover g. We'll call this the recovered g of u by just taking what I got out, this f of u, and divide it point by point by the kernel h of u. So this then is a deconvolution operation. And this is very exciting. If we can do deconvolution, then we can do things like we can sharpen microscope images and so on. So let's try to do the deconvolution. So we start out with this filtered g of x, and we take its Fourier transform, and there it is. And we see what we saw before. At high frequencies, g of u is all 0. Now, to recover, we want to divide by h of u. So here is the reciprocal of h of u. I call it h prime of u. It starts here at 1, and it increases up to huge values. This is 2 times 10 to the 5th. And in fact, it would go on up to even higher values because remember the Gaussian is rolling this off to very close to 0. And I actually had to limit how high it would go or else I would have numerical problems in the computer. So I can go back and ask what the corresponding kernel is, and it looks like that. So to do a deconvolution, what I'm going to do is I'm going to do a convolution with this bizarre inverse kernel. And the inverse kernel is this guy. Or equivalently, the Fourier transform looks like this. So here's the product. So I multiply these two together. And you can see this limit here means that I don't recover all of the high frequencies, but I recover a bunch of them. And if I transform back, then this is my deconvoluted result. So I've plotted the original signal in red here and my deconvolution in white. And you can see that I managed to recover the random signal pretty well. I managed to recover the square pulse pretty well. It kind of blew up in recovering the delta function. And this is just an example of how, in general, deconvolution is a difficult problem. Okay, now the next topic I want to talk about is something called the sampling function. In fact, it goes by various names. The sampling function, the Shaw function, or the Dirac-Combe function. Has fancy names because it's kind of an interesting function. I'll just show you what it is. So this thing, I'm going to call it, this is Shaw of x. Shaw is the Russian letter that kind of looks like what the function looks like. As you'll see in a minute, Shaw of x looks like this. It is there's a delta function at x equals 0. This is Shaw of x. There's a delta function at x equals 1. There's a delta function at x equals 2, and so on. And there's also a delta function at x equals minus 1, delta function at x equals minus 2. And these go on to infinity. So Shaw of x is equal to the sum over n from minus infinity to infinity delta of x minus n. So it's an infinite series of delta functions, all spaced 1 unit apart along the x direction. What we now want to know is what's the Fourier transform of this monstrosity? Well, okay, so we can begin to think about what the Fourier transform is by making use of the Fourier transform of a delta function, which is just 1. It's independent of u, and the shift theorem. So the Fourier transform of this Shaw function, I'll call it g of u, is going to look like this. It's going to look like 1 if I just look at this delta function in the middle. And then if I look at that delta function, which is shifted by 1 unit, so it's going to be delta of x minus 1, that's going to be e to the minus I 2 pi u times 1. And then if I look at that delta function, that's going to be e to the plus I 2 pi u times 1. And then I'm going to have the whole same thing, e to the minus I 2 pi u times 2, and the same thing with the opposite sign. Now you notice that we've encountered the same issue that I just talked about in the case of our homework problem, which is we're summing together pairs of complex exponentials with just flipping the sign of the exponents. So these are actually complex conjugates of each other, and so this really looks something like 1 plus 2 times cosine of 2 pi u plus another 2 cosine of 2 pi times 2u plus, and that goes on forever and ever. Okay, so that's what the Fourier transform of the Shaw function should look like. It looks like that. So it's not easy to prove, so I'm going to give you a numerical example. So here are three delta functions, the delta function at 0 and at +1 and at -1. So I've just picked up this much of this infinite series of terms. And there it is. It's 1 plus 2 times the cosine, with the cosine having a period of 1 unit. Then I add in some more delta functions, and I get this cosine sharpening up, and I have a value close to 0 in between, and I have this delta function-like thing that is getting very narrow and sharp. And as I add in even more and more of these delta functions, I'm going up to from -200 to +200, I get something that is looking more and more like a delta function. Remember the properties of a delta function. If we take its integral is equal to 1. And so if we just take the integral on this interval -1/2 to +1/2, we get the value 1. It is 0 everywhere except at its center, and at its center its value is infinite. But we haven't summed infinitely many terms, and also in order to get this get rid of the ripples that you saw, I had to do a regularization in the form of making a Gaussian envelope on this. But I can properly take the limit and make this Gaussian broader and broader, and in the end, we know that the Fourier transform of the Shaw function is just another Shaw function. So we can add one more entry into our list of Fourier transform pairs, and that entry is that Shaw of x transforms to Shaw of u. So there are actually exactly two functions where the function and its Fourier transform are the same. One is the Gaussian, and the other is the Shaw function, otherwise known as the Dirac-Combe function. It's a comb made out of Dirac delta functions, and in a minute we'll see why I call it the sampling function. Now it's kind of interesting to think about what is the convolution of some other function with the Shaw function. For example, let's ask what is the convolution of the Shaw function, Shaw of x, convolved with some other function. I'll call this h of x. And so there's Shaw, and here is h. And let's say that h of x as a function of x is some kind of thing that looks like that. Now, what's the convolution of these two? Well, if you think about the convolution integral, you can see that if I put a delta function as one of those functions, something special is going to happen. And the special thing that is going to happen is that I'm just going to get a copy of h of x in the output. So this is now my f, which is Shaw convolved with h. I will get a copy of this from the delta function at 0, but if I now put in this delta function here, it's going to give me another copy of h. It's just going to be displaced over here by 1 unit. And as I consider the infinite number of delta functions that make up the Shaw function, I get many, many copies of my h function, all just centered on integer values, 0, 1, 2, and so on. So the effect of a convolution with the Shaw function is to make many, many copies of our little function. So I just told you what is the what it looks like to convolve SHA with some function, but what's happening to the Fourier transform? So let's let h of u be some kind of function that maybe looks like that, and the convolution of SHA with h is going to look like the product of some kind of SHA function times h of u. And in this case, the SHA that we're going to be using is going to be then something that looks like a whole lot of delta functions, because what we're doing is we're taking the sampling function, which has delta function at regular positions along the x-axis, and the only points at which f has a non-zero value is the points where the SHA function has a delta function. So let me show you this in a numerical calculation here. Here is our starting our original function g of x, and we know from our problem set that the Fourier transform of that is going to be this oscillating object. Now, if I multiply g of x by a SHA function, and in this case it's a SHA function where the argument is 4 times x, so that means that in each unit interval on the x-axis, I have 4 delta functions, and so I've just multiplied this SHA function by my input function, and I get this series of delta functions. So we think about that as saying we are sampling this product, or we're sampling the function g of x at these discrete points. Now, the trick is that we know what the Fourier transform of something like that looks like. This is the product of g and the SHA function. And so in the Fourier domain, that product turns into a convolution. So what we have here is the convolution of my original Fourier transform times a set of delta functions that gives me a lattice full of copies of the original g of u function. I picked a particular sampling interval. I said the SHA of 4x. So every quarter of a unit along the x-axis, we have one of these delta functions. And it turns out that the units work out in such a way that then the spacing between these copies of the Fourier transform are exactly 4 units. So this should be looking to you a whole lot like a crystal. This is a infinite repeating lattice, and at each lattice point there is some kind of density, and this repeating lattice, if we Fourier transform in the other direction, we get a bunch of delta functions that are kind of like 1D spots, and so we're actually sort of doing crystallography in 1 dimension. Now, what's really interesting here is that we have these repeating copies of our original g of u, and if the g of u is completely contained in a particular region of the u-axis, then I can do a trick. The trick is this. I just set to 0 all of the extra copies of g of u, so that I have only 1 copy of g of u in the center. I can do that if I know that this function is indeed 0 at the points halfway between the copies. That is, if I say that this product, g of u times g of u convolved with the SHA function at a periodicity of 4, if I assume that there are no frequency components, that this value is 0 outside of this limited range, then what I can do is I can just force the value to be 0 outside of this limited range. I can take the inverse Fourier transform, and what I get is a smooth curve that looks exactly like the original, even though we threw away a whole lot of information. We start out with this continuous function, and then we multiplied it by a sampling function so that we have just this series of delta functions. And so we don't know anything about the values that the function took in between those delta functions. Nevertheless, by doing this trick, by saying, OK, I'm going to just set everything outside of this interval to 0, I can then do an inverse Fourier transform and get a perfectly smooth reconstruction of the original function. So this is called the sampling theorem, and we're going to see now why it's a big issue. Suppose I were to sample a little bit more slowly. So I'm going to sample only twice per unit on the x line, and I take the Fourier transform. Now the nicely separated copies of G of U are no longer nicely separated. They're beginning to overlap, and if I now set everything to 0 outside of one copy of that, I get a reconstruction, but it's not perfect. And if I sample even more slowly, then the reconstruction is worse. So in the ideal situation, where G of U decays to 0 and remains negligible and remains very close to 0, then what we can do is we can just cut out this part of the function and inverse transform it, and we've got the smooth function back. So what is going to be the criterion by which we set the sampling rate? Well, it's going to be the criterion where there is no overlap between the Fourier transform in the origin with the Fourier transform displaced by 1 unit on either side. Because if there is overlap, we get a phenomenon called aliasing. Aliasing means there is a component that belongs to a particular Fourier frequency, U, that actually appears at the wrong point on the U axis because we are adding together the Fourier components from different copies of this Fourier transform. So in this case, the relevant value is this U equals 2 and U equals minus 2. These are critical sampling rates such that we can make essentially perfect reconstruction of our sampled function. And if I sample too slowly, I cannot make a perfect reconstruction because I have overlap between these two copies of the Fourier transform, and hence we get errors. So this says then that there is a very special sampling rate below which we cannot do a complete reconstruction of our original function. And the sampling rate is called the Nyquist sampling rate, and the highest frequency to which we can validly expect our information to be correct is called the Nyquist frequency. So here's how it works. So let's suppose these are my copies of the original G of U, and so this band here is going to be plus or minus U naught, the frequency range over which I can expect that there is not going to be aliasing, and therefore that I can use in doing a reconstruction. And it turns out that this frequency U naught goes by the name the Nyquist frequency. And the Nyquist frequency is just equal to the sampling frequency divided by 2. So the sampling frequency, of course, is the periodicity in the Fourier transform. And so the sampling theorem says if we sample some function f of x at a rate of us, then Fourier components at frequencies less than u naught are preserved. So this was first noticed by Harry Nyquist in the 1920s, and the sampling theorem now goes by the name of the Shannon-Nyquist sampling theorem, and it's actually a remarkable result. It says that you give me relatively sparse values of a function, and I can, by doing these tricks, reconstruct the original smooth function, with the only caveat being that smooth function has to have no Fourier components too far out. So this is what we've talked about today. We've talked about the Shaw function, and the Shaw function is the fourth of the four Fourier transform pairs that we're going to be using. This is the new Fourier transform property, the convolution theorem, and I've mentioned the sampling theorem, which says that you can reconstruct a function like what I've shown here in blue from samples, like the white dots that I've shown here. Finally, I didn't want to leave you without another bit of homework, so here's homework for next time. Let's suppose that we have a filter, and the filter has this filtering kernel, and the input to the filter is a Gaussian function. And the question is, well, what is the output of the filter? So I'll give you a hint, which is that the output of the Gaussian, the output of the filter, the convolution of G and H, is going to be another Gaussian. And what's going to be really interesting is, well, what is going to be the width of that Gaussian? So this is just like the point where you take some kind of measurement, and maybe you filtered it with a Gaussian filter, and then you say, oh, I want to filter it some more. So I pass the result through another Gaussian filter. And then when you're writing the paper, you want to say, okay, so what was the net filter that I used? That's the answer to this question. See you next time.